So last time I explained what a limit is fairly informally and how you can compute them. And this time we're going to go over a much more formal definition of a limit and how you can prove that a limit is a certain number using this formal definition. So let's review the definition we had last time, which is that when we say that the limit of f of x as x approaches a is L, what we mean is that x is close to a but not a, then f of x is close to L. So this is the definition we were working with last time, and let's try and make this much more formal. So let's start with this is close to part. Now when we say that one number is close to another number, what we mean is the distance between them is small. And for this is small part, we can turn this into an inequality. We can say that it's less than some small number. And the number we're going to choose here, it's going to be a variable. We're going to draw it like this, and we're going to call this variable delta. Now we're actually going to explain what delta represents in a sec, but for now just think of this as some small number. Now if we want to incorporate this x not equal to a part, what we need to say is that the distance between them is greater than 0. So now this expression is looking a lot better, but we can still improve this middle bit here to make it a bit more mathematical. So if we want to represent this expression here more mathematically, it's going to require a bit of a tangent about how we can represent distances in math. So finding the distance between two numbers is something I'm sure you guys know how to do, even though you've probably never thought about an exact formula for how to do it. But if I tell you what is the distance between 10 and 4, it would be pretty easy to say that this is 6. And then if I asked how you calculated that, you would say, well, it's just 10 minus 4. But then if I asked for the distance between 3 and 11, this distance is going to be 8. And the formula for this one is 11 minus 3. So if you were to try and create a general formula for the distance between the numbers a and b, you'd probably say it's a minus b if a greater than b, and b minus a if b greater than a. However, we can actually condense these two formulas down into one formula by using the absolute value function. So if we want to find the distance between two numbers in general, it's just going to be one number subtract the other number. And in this formula, it doesn't matter which number is bigger or what order we put the numbers into the equation. So if I want to talk about the distance between x and a being greater than 0 and less than delta, that is the same as saying that 0 less than absolute value of x minus a less than delta. And now there are some important manipulations that we can do with this inequality, which are going to be very useful when we're doing proofs involving this formal definition of limit. So since absolute values are kind of restrictive in how we can work with them, we can get rid of this absolute value by breaking this inequality down into two cases. So to keep this overall inequality true, if x is greater than a, then this thing in here is going to be positive, so the absolute value of this expression is just that expression. So in that case, we just have the distance between x and a being greater than 0, less than delta. And then if we have a scenario where a is greater than x, and we want to write it out as an inequality without absolute values, what we actually need is for a minus x to be less than 0 and for it to be greater than negative delta. So this one inequality up here and these two inequalities down here are equivalent. And then if we want to condense these two back into one without the absolute value, we can just kind of merge this chunk and this chunk together. And we'll end up with x minus a being greater than negative delta and less than positive delta. So this inequality being true up here implies that this one is also true. However, we can't forget about this 0 case. So since delta is a positive number, notice that 0 is in this interval between delta and minus delta. So we have to include a separate case for x being equal to a to make sure to keep 0 out of this interval. So this inequality right here is equivalent to this inequality down here. And if we omit this x equals a case, then this top inequality implies this second inequality. It's just not true in the reverse. If we include the case x equals a, then the expressions are entirely equivalent. But working with just the one-directional form of this inequality, we can actually manipulate this a bit further. If we want to solve for x in this inequality, what we can do is we can add a to each part, and we're going to end up with x being between a minus delta and a plus delta. So these two inequalities are equivalent. And this last inequality is very useful for visual representations. When we're saying x is in this interval, what we mean is that we have a point A, and then we have the point a minus delta, and then we have the point a plus delta. And if this inequality is true, it means x is somewhere in here. So keep all of these manipulations you can do with inequalities in mind, because they're going to come in very handy later on when we get into proofs involving the formal definition of limit. And one more important thing to know about the absolute value function is it has two properties that are going to come in handy when we do proofs involving the formal definition of a limit. So one is that the absolute value of a product is the same as the product of the absolute values, and the absolute value of a sum is less than or equal to the sum of the absolute values. So back to the definition we had. We can rewrite this as if the absolute value of x minus a is greater than 0 and less than delta, then f of x is close to L. And using the exact same workings, we can rewrite this expression as well. This is equivalent to saying that the absolute value of f of x minus L is less than some small number. And I'm going to use epsilon to represent the small number. Notice that delta and epsilon don't represent the same thing. It doesn't have to be the case that when x is a certain distance from A, f of x is that same distance from L. They just have to be both fairly close by, but it doesn't have to be exact. Also notice that in this second one, we don't need to include the case x equals A, because in the limit, it's totally fine if f of x is exactly equal to L. Like if we have the function f of x equals 1 and we calculate the limit at 2, it's just 1 the whole time, including as it approaches 2. So this expression is now looking a lot more formal, and notice that this if-then, we can rewrite this as just a conditional. And now we have a much more mathematical definition for the limit. However, there's still the issue, which is that we haven't defined what exactly delta and epsilon are. And to do that, it's going to help to draw a picture. So if I have some function here and I'm trying to find the limit as x approaches A, looking at this picture, we can see that limit is going to be this number right here. Let's call it L. And so for now, just setting one specific value of delta and one specific value of epsilon, we can use the manipulations we saw previously So looking at this expression above with the specific values of delta and epsilon we chose, what this statement is saying is that if we have some x value that's inside this interval here, then the corresponding f of x value has to be inside this interval here. Notice that if we have an x value outside of this interval, it doesn't really matter what the corresponding f of x value is. All that matters is that if we have an f of x value in here, then the corresponding f of x value can't be inside this box or inside this box. So now, notice that just satisfying this implication for one specific value of delta and one specific value of epsilon does not guarantee that the limit is going to be L. Notice that we could draw a function f of x where at the point A, the value of the function is any number, and as long as we don't let the function enter these forbidden regions, we're still going to see that every f of x value is between L plus epsilon and L minus epsilon. So in this example, the limit would be this number right here, but then we can draw a different number, a different function where the limit is this number right here. So it's clear that we're going to have to take multiple epsilons and multiple deltas. But which one should we restrict first? Well, notice that if we take a smaller delta, so now if we create some new interval, a minus delta 2 and a plus delta 2, this actually hasn't restricted what the limit of the function is at all. All it's done is it's shrunk these, all it's done is it's shrunk the forbidden regions down, but we see that the limit can still be any number between L plus epsilon and L minus epsilon. If we shrink epsilon, on the other hand, then as epsilon gets smaller and smaller, notice that we're limiting the range the function can be in more and more. For instance, for this new smaller epsilon, the limit of the function can only be a number inside this box right here, as opposed to the previous one where it could have been any number inside this box right here. So it seems that as we take smaller and smaller epsilons, we're going to restrict this value more and more and more. And eventually, we're going to end up concluding that the only value that the limit can be is L. Now, it would be convenient if we could just set epsilon to be the single smallest possible positive number. Then we'd end up with a radius around L that's infinitely small. So we could immediately restrict the value of the limit to only being L. But of course, there's no such thing as the smallest possible positive number. Instead, we have to allow any positive value for epsilon. But we know that when we're thinking about the limit, the important values are the really, really small ones. On the other hand, for delta, it doesn't really matter how small the radius around A is. For instance, if we have this function, we know that the limit as x approaches A is L. So if we want to verify this using this implication up here, we know that we're going to have to be taking increasingly smaller values of epsilon. Like if we take this one, what we need to do is we need to find one specific value of delta where we can create this box where all of the values of the function are outside the forbidden regions. If we take a smaller interval, what we need to do is we need to find a new delta to create a new box that keeps all the function values outside the forbidden regions. So this gives me a pretty clear picture of how we should introduce our delta and epsilon variables. What we're going to say is that for every positive epsilon, there exists some positive delta, such that if x is between the interval a plus delta and a minus delta, then f of x is in the interval L plus epsilon, L minus epsilon. So this is our complete formal definition of a limit. And notice that there's a bit of a hidden quantifier in here, which is that technically we should be specifying what x is. In this case, we want this inequality to be true for every real number x. But oftentimes, it's okay to omit this inequality since it's just assumed that you want this to hold for every real number x. But there's nothing wrong with including it. So here is our definition for the limit of f of x as x approaches a being L. But before we reach this point, we should explain what f of x, a, and L are. Let's first write that a and L are real numbers. We need to let f be a function defined at least on an interval containing A. And then remember that we actually don't need the function to be defined exactly at A. So we can say except may be at A. So this is the full definition with all of our constants and variables defined. And now we can also pretty easily define the concepts that we mentioned last time, which are limit as x approaches A from the left, and the limit as x approaches A from the right. And we can do this pretty easily by referring to the manipulations we did earlier with absolute values and the distances between numbers. So for the second definition, our assumptions are going to be mostly the same, except this time A does not have to be on the interior of our interval. Last time when we were referring to an interval containing A, what we're thinking about is some kind of open and or closed interval where we have some number here and some number here, and these numbers are not A. A is like somewhere in the middle here. But in this new scenario, it is okay for A to be at one of the endpoints. Like for example, if we have this function here that's defined only for negative values, this function still has a limit as x approaches 0 from the left, even though 0 is the endpoint of the interval that the function is defined on. So the way we can notate this is that f is a function defined on an interval a minus some variable. I'm going to call it b a. And then we have to define what b is, and b is just any positive number. So these are our new assumptions, and if we write out our new definition, we're going to start out with the same. For every epsilon positive, there exists a delta positive, such that, and then for this component here, so we know that since we're approaching from the left, A is going to be greater than X. So this expression here is going to be negative. And how negative do we want it? Well, we want it to be less negative than negative delta, as per our workings up here. So writing that out, we want that negative delta to be greater than x minus a to be less than 0. And doing a bit of rearranging, we can rewrite this as 0 less than a minus x less than delta. So let's use this inequality instead, since it looks a bit nicer to have positive delta as opposed to negative delta. And this being true implies that the absolute value of the distance, this implies that the distance between f of x and L is less than epsilon. So this is our definition for approaching the limit on the left, and we can do pretty much the same thing for the limit on the right. So this is the definition for the limit of f of x approaching a on the right being L. And these are all our necessary assumptions. Definition, and now the last kind of limit we can define now is that the limit does not exist. So when we say that the limit as x approaches a of f of x does not exist, what we mean is that for every L, this limit is not equal to L. So the way this definition is going to work is we want to say for every real number L, this statement is not true. So we need to negate this statement here. And the way you do that is, for the most part, we're just going to be flipping around all of these quantifiers. And then the way you negate a conditional is you say that the if part is true and the then part is false. So this here is the definition that the limit at a point A does not exist. Okay, so let's see some examples of how to use this definition to prove a limit. Let's try and prove that the limit of the function 2x plus 1 as x approaches 3 equals 7. So let's write out the statement that we want to prove. What we want to prove is that for every positive epsilon, there exists a positive delta, such that if the distance between x and 3 is less than delta, then the distance between 2x plus 1 and 7 is less than epsilon. So looking at the structure of how this proof is going to work, we're going to first fix some positive epsilon. Then we're going to choose a value for delta. Then we're going to fix some real number x and assume that the absolute value of x minus 3 is between 0 and delta. Then we're going to do some algebra, and we're going to conclude that the distance between 2x plus 1 and 7 is less than epsilon. The main difficulty we're going to run into with this proof is figuring out what value of delta we should take. So let's do some rough work to try and figure that out. So our goal is to show that 2x plus 1 minus 7 is less than epsilon. And we know that x minus 3 is less than delta. So let's manipulate this a little bit. This is the same as saying that 2x minus 6 is less than epsilon. So now we can factor a 2 out of this expression. So we get 2 times, so we get that the absolute value of 2 times x minus 3 is less than epsilon. Then we know that, and now we know that the absolute value of a product is the product of the absolute values. And the absolute value of 2 is just 2. So we now see that showing this right here is the same as showing this right here. And this is useful because this x minus 3 looks familiar. Earlier on in the proof, we're going to assume that this is less than delta. So we know that this expression right here is less than 2 times delta. And what we want to show is that this is less than epsilon. So what if we pick the value of epsilon over 2 for delta? Then we know that assuming this is less than 2 delta is the same as assuming this is less than 2 times epsilon over 2, which equals epsilon. And we're going to end up with the inequality that we want, this being less than epsilon. So that concludes our rough work. Now we can fill in the details of the proof. So going back to the outline we had before, let's take delta to be epsilon over 2. Now we fix our x, and we assume that absolute value of x minus 3 is less than delta. Now we know that 2x plus 1 minus 7 equals 2x minus 6, absolute value, which is the same as 2 times x minus 3, which we know is less than 2 times delta, which equals epsilon via our choice of delta. So let's see a harder example. Let's try and prove that the limit as x approaches 4 of x squared plus 1 equals 17. So the structure of the proof is going to be the same. So let's do some rough work to figure out what value we should take as delta. So let's start with the inequality we'll want to prove. So this is the same as x squared minus 16, and now we can factor this expression. This is going to factor into x minus 4 and x plus 4. And then the absolute value of a product is the product of the absolute values. And now we're in a similar scenario as we were in previously, where this bit right here looks familiar. It's our assumption. So we know that this expression here is less than delta times x plus 4. And we want to show that this expression is less than epsilon. So you might think that let's take delta equals epsilon over x plus 4. So then these two will cancel and we'll end up showing this is less than epsilon. However, this right here is not allowed. And the reason is because looking at the structure of our proof, we see that we have to take delta before we choose the value of x, meaning we can take delta based on epsilon, but we can't take it based on x. So we're going to have to come up with a new idea. So everything up to this point in our rough work was entirely correct. And in our final solution, we're still going to want to rewrite this expression as epsilon over some number. And if we can conclude that this number is greater than x over 4, then we can still end up with the inequality that this is less than epsilon, which would be sufficient to complete the proof. So what we really need to do is we need to find some number c such that x plus 4 is always going to be less than c. Now you might think this is impossible. Since x can be any real number, this expression right here is going to get infinitely big, so we can't bound it below by something. But remember that the values that x can be is not completely unlimited. It has to be the case that the absolute value of x minus 4 is less than delta by our assumption. So this makes me think, what if we create some kind of max value for delta? That will also create a max value for x, and then we can find a max value for this expression. So let's take delta to be at most 1. We could have chosen any number to be the maximum for delta, but 1 makes this pretty easy. So now in our assumption, we're going to assume that this inequality is true. And this is very helpful because it lets us isolate for x. Using the manipulations we saw earlier, we know that this implies that x minus 4 is between 1 and negative 1. So x is between 3 and 5. And there we go. We found that x has to be less than 5. So going back to this expression here, we know that x plus 4 is less than absolute value of 5 plus 4, which equals 9. Meaning, going back to our rough work, we can put a 9 down here, and we know that this expression is less than epsilon times absolute value of x plus 4 divided by 9. We know that this is less than 9, so since this number is bigger than this number, then this whole expression is less than just epsilon by itself. So, looking back at all the assumptions we had to use to make this necessary, what we needed was that for delta to be at most 1, and for delta to be at most epsilon over 9. So the way we can satisfy both these expressions at the same time is by taking delta to be the minimum of 1 and epsilon over 9. So that is going to be the value for delta that I'm going to pick. So starting with this section, let's copy the algebra we had. And now we can write that we know that since delta is less than or equal to 1, x minus 4 is less than 1. So x is between 3 and 5, and x plus 4 is between 7 and 9. Thus, x plus 4 times delta is less than 9 times delta, which is less than or equal to 9 times epsilon over 9 by our choice of delta, which equals epsilon. So we have found that our original inequality is less than epsilon, and that's all we needed to do. So let's do one more example, this time proving that a limit does not exist using the formal definition. So let's prove that the limit as x approaches 0 of x over absolute value x does not exist. So remember that the absolute value function can be broken down into two cases. This function is x if x is greater than or equal to 0, and negative x if x less than 0. So we can split this function down into two cases. This function is x over x if x greater than 0, and x over negative x if x less than 0. So the graph of it looks like this. We have a line at -1, and we have a line at 1. And at 0, the function is undefined. So we can see that the left-hand limit and the right-hand limit don't agree, so this limit at 0 does not exist. And if we want to go prove that using the formal definition, what we need to prove is that for every real number L, there exists a positive epsilon such that for every positive delta, there exists some real number x such that the distance between x and 0 is less than delta, and the distance between x over absolute value x and L is greater than epsilon. So for the structure of our proof, we're going to fix some real number L. Then we're going to choose some epsilon. Then we're going to let delta be some positive number. Then we get to take an x value of our choice. And then we need to show that both the absolute value of x is less than delta and the distance between our function and L is greater than epsilon. So let's do some rough work to figure out what we should take for these two variables. If we draw a picture, the way this proof is going to work is we're going to have some random L. Like let's say we have this L right here. Then we get to choose what we want our radius to be. Like if we choose a radius like this. Then some random delta is going to be fixed. Let's say we end up with this delta. And what we need to do is that we need to choose some x value where x is inside this delta radius and outside of this epsilon radius. So if we chose this value of x right here, this would prove that the limit of this function is not equal to L. Then we just need to repeat that process for every L. Thinking about what kind of epsilon value we should take, there's actually a whole host of options that work. For instance, if we take epsilon equals 1, then what we can conclude is at most one part of the function is going to be within this radius between L minus 1 and L plus 1. Like if we have some really huge value for L, then obviously both parts of the function are going to be outside that radius. If we have some huge negative value, both parts are going to be outside. And if we have some value inside, like if we have L is 0, then again, we're going to have both parts of the function being outside the radius, because remember, our radius is an open interval. We're considering the interval from L minus epsilon to L plus epsilon, not including these endpoints. What we should do is we should fix some L. We can take epsilon equals 1, and then we can split it into two cases. If L is some positive number, then let's just take any x inside our delta radius. And that delta is always going to exist, and we know that value of x is always going to exist, even when delta is random, because remember, it has to be a random positive number. So the radius between negative delta and delta is not the empty set. Conversely, if we have some negative value for L, we can just choose any x value on the interval from 0 to delta. And then we know that that corresponding f of x value is going to be outside our radius, L plus 1 and L minus 1. So this is the rough idea of the proof. Filling in the details, we can take epsilon to be 1. Then let's fix our positive delta, and let's describe the two cases we just discussed. So we know at least one of the following is true. Either 1 is not an element of the open interval L minus 1, L plus 1, or negative 1 is not an element of the interval L minus 1, L plus 1. So, this will dictate how we take x. So let's take x to be an element of the interval 0 to delta if case A is true, and x to be an element of the interval negative delta 0 if case B is true. Now there are two inequalities we need to satisfy. First, we need to show that the absolute value of x is between 0 and delta, and then we need to show that the absolute value of x divided by absolute value of x minus L is greater than 1 by our choice of epsilon. So the first inequality is going to be quite simple. We can say since x is between negative delta and delta by our choice of x, then the absolute value of x is less than delta. Also, notice that we did not allow x to be 0, since both of these are open intervals. So we can say that also since 0 is not an element of 0 to delta open, and zero is not an element of negative delta 0, then we know that the absolute value of x is going to be greater than 0. So that proves the first inequality. Now for the second one, let's bring back the two cases we had earlier. So let's say if case A is true, then we're going to take x to be an element of 0 delta, and we know that x over absolute value of x is going to be equal to x over x, since x is a positive number, which equals 1, which we know is not an element of the interval L minus 1, L plus 1. And then remember, the ultimate inequality that we want is that the absolute value of x divided by absolute value of x minus L is greater than 1. And the way we can get from here to here is by, again, breaking this into cases. So notice that saying 1 is not an element of this interval means either one of two things. Either 1 is greater than L plus 1, or 1 is less than L minus 1. So let's say, more specifically, one of the following is true. 1 is greater than L plus 1, or 1 is less than L minus 1. Starting with the first one, we know that this implies that 1 minus L is greater than 1, which implies that the absolute value of 1 minus L is greater than 1. And the reason why we can do this last implication is because right here we've said that this expression right here is positive. So you can just take the absolute value of a positive number and you're not going to change anything. And recall that this is sufficient to complete the proof because 1 is exactly the value of x over absolute value of x for all positive x values. Looking at our second scenario, the other way that 1 is not an element of this interval is for 1 to be less than L minus 1, which implies that L is greater than 2. So if we consider the equation absolute value of 1 minus L, well, this is equal to the absolute value of L minus 1. This is by the property that the distance between A and B is the same as the distance between B and A, as per our workings earlier. And then, since L is greater than 2, this term here is going to be positive. So this equals L minus 1 without the absolute values, which we know right here is greater than 1. And these bits right here are precisely what we wanted to show. Because remember, evaluating this function for any x greater than 0 is just 1. So we can say in both cases, the absolute value of x divided by absolute value of x minus L is greater than 1. And now we have to consider the case where B is true, which is going to be very similar.